Hey, Hoodie Math welcomes you back on this great adventure. We're going to try to get through these inverse Laplace transforms, these elusive mythical creatures. We're going to go travel through the jungle of math and see if we can unravel some of the mysteries of the transform. We begin our adventure now. We're trying to find the inverse transform of the following Laplace function, and so I hope you have your handy dandy table of Laplace transforms. And example number one, we're going to find the elusive 1 over s constant along with the 1 over s minus a, which is our exponential e to the at hoodie with a boogie. All right, here we go. So we have to identify this as our constant. Constant. Already messed up in the beginning. I'm not starting over. And this is our e to the at. So just identifying those numbers on top as constants. If this was our s plus a, it still matches. We just know that we have a negative exponent then. So f of s is our Laplace transform. That means f of t was our original. 6 over s, it matches with our constant, which is 1 over s. This could be written as such. So it would just be 6 in front of our constant, which is just itself. Minus e to the at. Again, noticing that it's 1 over s minus a. A is 8, so it's, you guessed it, e to the at. Why is there a minus sign in front? Well, there's a minus sign right there. Plus, 4 is a constant. Again, 1 over s minus 3. 4 is in front. You'll see me do that a lot in this video. So 4 is the constant, 3 is the a, and so e to the 3t. And that was the original function before our transform. That's numero uno. We're going to go through, I think, 1 through 5 or 1 through 6 in this here video. Let's move on to number 2. So again, transforming, we're trying to identify those Laplace transforms. Another exponential, e to the at. We have a weird 3 in front, but it still looks like e to the at if we can somehow adjust these numbers to match. The third term, 7 over s to the 5. Now that's different. Haven't seen that. What could that be? Yeah, it's t to the n. It's number 3. So think about this being 7 in front, 1 over s to the 5. And remember that if n plus 1 is 5, remember our original function was n factorial over s to the n plus 1. Oh, missing that n factorial part, right? Remember derivatives and rewriting. So if n plus 1 is 5, and that's what I've written here, then n must be 4. Well, what is 4 factorial? And then what is s to the 4 plus 1? That's what we're trying to transform. So now we know the n is 4. What was 4 factorial? Well, it's 4 times 3 times 2. You can write it out as 24, which I'm going to go ahead and do. So 4 times 3 times 2 times 1 is 24. So I'm going to have to count for that, just like a derivative. If 4 factorial was supposed to be on top, I must have divided it out, which means that at the end term, 7 being the constant, there'll be a 24 on the bottom, and this term will then be 2 to the n, which is just 2 to the 4. So that's the ending term that I just elaborated for you. Let's go back and find some of these other pieces. So again, this is just going to be, I'll write it over here, 19 times some 1 over s plus 2. And if you want to write that a little bit differently, with the transform s minus negative 2, if you really want to identify that a term, which is negative 2. So leaving myself plenty of room, f of t equals 19 constant. S plus 2 matches with s minus negative 2, which is e to the at. A being negative 2 for this here term. So 19 e to the negative 2t. So what are we going to do with this guy? So I'm just going to take him off to the side and see if we can do a little factoring. So what if I was to take a 1/3 out? Well, if I had a 1/3 out of this problem, then I'd have an s. Well, I'm taking a 3 out of the bottom, right? So I'd have an s minus 5/3 or 15. 5/3. Because 3 multiplying back in would give you this, right? All right, so that's my 1/3. This is my constant in front, my coefficient, and this is my here a. So it's going to be positive 5/3. 1/3 in front, so minus 1/3 e to the 5/3 t. And there's our transform. So I know I did that kind of out of order. Hopefully that made sense. If it's still matching with an exponential, you can factor out the 1/3, make that a 5/3. That's our new a. And there we go. We got a Laplace transform. Found them. Crikey. Moving on to number 3. Number 3. All right, f of s. We have our Laplace transform. These look different again, as they should. We're practicing new problems. 6s. Well, maybe I can rewrite it. Let's look at this guy. Maybe I can rewrite him. Those are close, but this one has a variable and this one doesn't. Sorry for the huns. All right, look at sine and cosine. Looking at our table here, 7, that's your sine. That's a constant on top, and your constant matching here. That's going to be important to divide out. And then again, variable here, constant. All right, so the first one is cosine, because we have our constant on top, and this one's going to be our sine transform. All right, so what do we need with our cosine? How do we get it back? Well, we need a cosine a. We need to figure out what a is, right? And then we need to make sure we rewrite it as such. In this one, a would be 5 squared. So a is 5, and the same thing here, a is going to be 5. So I'm going to write the first term, f of t equals, 6 is our constant, times cosine, and a is 5, cosine 5t. That's the first term. Now let's do the Laplace transform for the second term. We see there's got to be a 3 of some sort, right? But again, remembering our formula from 7, there has to be the a on top. Well, if a is 5 and it's not showing on top, guess what we do? We're putting that 5 in the bottom to account for it. Cool. Again, a being 5. So 3/5 sine 5t. So just kind of like derivatives, when you solve for u and du, you're getting those extra terms. It's kind of akin or similar to what we have here with that constant being on top. If it's not there, guess what? We're going to make it go there, because then 5 over 1/5, right? So if it's 5, if I put 5 there, then I put a 5 there, and now the formula matches, and a is 5. And we get our transform. All right, so there's number 3. Done. Moving on. 2, 4. All right, so number 4, again, we're trying to match these functions with something that's on the table, something we're familiar with. That's why the more you see the table and understand the basics of it, we get to identify a little bit faster, kind of like knowing your times tables when you're factoring. Pretty important. All right, so looking at number 4, we have 8 over 3s squared plus 12. Maybe I can rewrite that with the 8 in front and the 3 in front. That seems like something I should do. That I would have a 1 on top, and if I took the 3 at the bottom, I have s squared plus 4. That looks great, because now I have a square plus a square. Do I have that match anywhere? Oh, it's kind of like the problem we just did, isn't it? The sine. So this is going to be sine 1. What would a be? 2? 2 squared? All right. and then that means 2 must be on top. So if 2 is on top, then I have to give a 2 to the bottom, and that's going to be an 8/6. So my first term, f of t, will be 8/6. 2 times 3 is 6. That reduces to 4/3. 4/3 sine 2t. So this transforms into 4/3 sine 2t. Second term, let's look at taking maybe a 3 out. We have a 1 over s squared minus 49. Last one with a plus. There's a square here, so that's probably a good thing. Let's see if we can identify. Sine h at. Number 17. So on 17 we have a over s squared minus a squared. We just need to give a back to the top. A being 7. That means there needs to be a 7 here, and then a 7 here. So plus 3/7, and then sine h at 7t. And there's our Laplace transform. Back to our original. We are doing inverse Laplace transforms today, and that's what we're on. Let's move on to number 5. Ooh, there's a new one. This looks interesting. Looking through the tables, you may want to pause the video because I'm going to give it away in about 5 seconds. If you look through the table, you will not find it on the table, but you will need to write a version of this that might be on the table, because I know I've done something with a perfect square here, and couldn't we just call this right up here square root of 7 squared? Could we call it that? Absolutely we could. But the top doesn't match anything until we separate it. 6s over s squared plus 7 minus 5 over s squared plus 7. All right, so now it's starting to look a little bit closer to what we need. If I write this as 6 on the front, I'm going to write this as s squared plus the square root of 7 squared. So this would match with cosine, where a is the square root of 7. Again, you have your variable on top, something squared. Even though 7 is not a perfect square, you can write it as the square root of 7 squared. And so our new Laplace transform, f of t, would equal 6 is the coefficient in front that carries through, and as you said, it's cosine, square root 7t. So now we need to do the second part. So again, we have a perfect square. We're going to bring the 5 out in front. We're going to want a 1 on top. S squared plus square root of 7 squared. So what do we need here? Again, 1 can't be on top. It's got to be the square root of 7. Well, if I give a square root of 7 there, I got to give a square root of 7 there. And so we have minus 5 square root of 7. A being the square root of 7, this matching with sine square root of 7t. So hopefully you're kind of seeing the rhythm of these and how each problem kind of flows through, kind of similar to derivatives and rewriting, just keeping track of the equalities of each transform. Moving on to 6, last one for today's video. I'll finish up the notes in a second video. So, number 6. F of s equals 1 minus 3s. I didn't like that originally, and so I did this. It's like variables first, please. There's order here, right? This is not like we're living in coronavirus days. We do have order. We've done everything with perfect squares so far, and definitely this is not a perfect square in the bottom. So in order to do this problem, we want to separate, but it'd be way too early to separate now because of equalities. We want to transform this into a perfect square somehow. And whatever's left over, again, we can just write as the square root. Okay, so let's proceed. Sorry for that space between the -3 and s. Let's just put a times there so you know that they're still connected. All right, in the bottom, s squared plus 8s. What would the perfect square be? Making a perfect square here. Well, half of 8 is 4. 4 times 4 is 16. You got a different equation. You better know that. So if I add 16, I got to take away 16, correct? And then that plus 21 is still there. All right, so we have a perfect square now. Negative 3s plus 1 over, this is going to be s plus 4 squared minus 5. All right, we're getting closer. All right, minus 5, so plus 5. So thinking on the next step, what do I want to do? Well, if s plus 4 is my variable in the bottom, I better have that on top. Everything we've had in the bottom here has been on top if it's going to be a cosine since it's a variable. So let's put that there. I need an s plus 4 here. So I need an s plus 4 on top. So I'm really adding in a negative 12. Write that like in a different color here. I need a negative 12 there. So if I'm adding in a negative 12, to make it go back to 0, I need to add 12 and turn my phone off. And then I have that plus 1 there. All right, so let's rewrite this. Negative 3, s plus 4, plus 13, s plus 4 squared, plus 5. All right, so we're just rewriting this original Laplace transform. Haven't changed much yet. I'm just getting into a format that would blend with something on the table since nothing was there. All right, so now it's kind of like the last problem. Couldn't we separate this? Couldn't I separate this into negative 3, s plus 4? Oh, what am I doing? Oh, I put that in front. I get it. S plus 4 squared plus 5. So negative 3 is supposed to be in front. And then couldn't I put a plus 13 here times 1 over s plus 4 squared plus 5. And maybe yet square root of 5 squared. I fit that here, square root of 5 squared. All right, we're getting closer to something, I hope. All right, so what are we going to match this up with now? Does anybody see it? I sure don't see it. Just kidding. I've done this already. Number 20. I'm going to write out number 20. 20 said e to the at cosine bt is equal to s minus a over s minus a squared plus b squared. So that's what number 20 says. All right, so can we just identify some of these pieces then? All right, thank you for letting me do that. Okay. A is negative 4, s minus a, so negative 4. B is the square root of 5. So let's put that into our formula here. So f of t equals negative 3 e to the at. E to the negative 4t. Cosine bt. Cosine square root of 5t. All right, so that's the first part. Now let's identify the next part. I can guarantee there's going to be a 13 there. Might be something underneath, right? What would that one match with? And if you said 19, you would be correct. There's 19. Let me see if I can write that on this side as well. E to the at sine bt transforms into b over s minus a squared plus b squared. So identifying some of these pieces from our problem, I have negative 4 again for a. And b needs to be on top, so the square root of 5 is needed there, so I need it here. 13 over square root of 5, this is now this formula. So e to the at, e a is -4, -4t, sine bt, sine square root of 5. And there it is. There's the Laplace transform. So I think it's kind of fun. It's like new math in a different way, in a different mode. So hopefully you enjoyed that video. 20-minute video. That's why I only did first six problems. I'll do the next next few problems in the next video. Hope you guys are enjoying your mini break. As you guys become adults and learn to live life, you guys really got messed up with this coronavirus, didn't you? I feel bad for you guys. But be positivity. Find that happiness. You guys are great kids. Keep it going. Blackhawks out.